Welcome to today's episode of Days of Mass Extinction on planet Earth. Imagine standing on a beach 252 million years ago. The water around you is a sickly green, bubbling with toxic gases. The air burns your lungs as volcanic ash rains from blood red skies. You're witnessing the closest our planet has ever come to total biological annihilation, the Great Dying. But this isn't science fiction. This happened. And it's just one of 5 catastrophic events that have nearly erased life from Earth's surface. You think the asteroid that killed the dinosaurs was bad? That was nothing compared to what came before DOT in the 4.5 billion years since Earth formed. Life has faced 5 apocalyptic trials that paleontologists call the Big 5 mass extinction. Events so devastating, they rewrote the entire story of life on our planet. Each time, over 75% of all species vanished in what amounts to a geological heartbeat. Each time, the survivors rebuilt the world from scratch. Today, we stand at the threshold of a 6th mass extinction. But this time, there's a twist that makes it unlike anything Earth has experienced before. This time, a single species, us, is pulling the trigger. Over the next 2 hours, you'll journey through 500 million years of catastrophe and survival. From ancient oceans frozen solid to skies on fire, from the rise of the first complex life to the potential fall of our own civilization. You'll discover how 5 previous mass extinctions shaped the world you live in today, and why understanding them might be the key to preventing the 6th. The story begins where life itself began in the ancient seas. Chapter 1. When the seas turned to ice. Picture Earth 450 million years ago, and you wouldn't recognize it. No birds sing in the sky, because there are no birds, no animals of any kind live on land. No trees sway in the wind because forests haven't been invented yet. The continents are barren rock, as lifeless as Mars. But beneath the waves, life is exploding. The Ordovician period represents one of evolution's greatest success stories. In the sea, crinoids and their cousins, the blastoids, were having a heyday. Coral reefs stretch across tropical seas, teeming with creatures that look like something from an alien world. Trilobites, those iconic 3-lobed arthropods, scuttle across the seafloor in countless varieties, from tiny pillbugs to giants the size of dinner plates. Swimming above them, knot-lined cephalopods patrol the reefs like living submarines, some reaching lengths of 15 feet. The diversity is staggering. Brachiopods filter feed in vast beds. Graptolites drift through the water column like living newspapers, their colonial structures resembling pencil marks on stone. Sea lilies sway in underwater meadows that stretch to the horizon. Tonodonts tiny, eel-like vertebrates dart between the reef structures. These were all key members of the Paleozoic fauna. This underwater Eden represents the first great flourishing of complex life on Earth. For 40 million years, biodiversity exploded across the ocean floor. Then, in a geological instant, it all came crashing down. The killer came from an unexpected direction: the sky. But not in the way you might think. No asteroid struck Earth during the late Ordovician. Instead, something far more insidious began. Planets started to freeze. The icy onslaught may have been triggered by the rise of North America's Appalachian Mountains. The large-scale weathering of these freshly uplifted rocks sucked carbon dioxide out of the atmosphere and drastically cooled the planet. Imagine the carbon dioxide levels dropping so fast that the global thermostat crashed. Average temperatures plummeted by as much as 13 degrees Fahrenheit. But the real devastation came from what happened next. As a result, sea levels plummeted by hundreds of feet. Picture the coastlines you know today. Then imagine the water dropping so far that the continental shelf, the underwater plains that host most marine life, becomes dry land. Glaciers are made of water, and that water has to come from somewhere. As we are currently seeing in modern times, melting glaciers add water to the ocean, which raises sea level. The reverse is also true. At the height of the most recent ice age, sea level was approximately 120 meters lower. During the late Ordovician, the drop was even more catastrophic. The great supercontinent Gondwana drifted over the South Pole, and massive ice sheets began to form. As more and more water became locked in glacial ice, sea levels crashed by over 300 feet. The vast continental shelves that had been underwater paradises became exposed land. The shallow seas that supported 85% of all marine life simply vanished. For creatures that had evolved in warm, shallow waters, this was apocalyptic. This is bad news for marine invertebrates, most of which live in the shallow marine realm. Dropping sea level by more than 330 feet reduces the amount of habitat they have in which to dwell, and increases competition between individuals. The extinction unfolded in two deadly pulses. First, the cooling climate and falling sea levels devastated tropical species. Then, just as life was struggling to adapt, the Ice Age ended as suddenly as it began. Volcanoes and geological processes pumped greenhouse gases back into the atmosphere. The ice melted rapidly, and sea levels rose again, but the returning waters were different. Once sea levels started to rise again, marine oxygen levels fell, which in turn caused ocean waters to more readily hold onto dissolved toxic metals. The seas that had once been crystal clear became toxic soup. Hydrogen sulfide, the gas that gives rotten eggs their smell, bubbled up from the depths, poisoning the water and creating dead zones that stretched for thousands of miles. The numbers tell the story of devastation. Of the species paleontologists have documented, about 52% of them disappeared at the Ordovician-Silurian boundary, never to return. But the percentage doesn't capture the full horror. The extinction event suppressed many of these changes, eliminating some 71% of all species living right before the event. Entire groups of organisms that had dominated the seas for millions of years simply vanished. Massive reef-building organisms called stromatoporoids went extinct. Many types of trilobites disappeared forever. The graceful graptolites, once so common their fossils define rock layers around the world, were devastated. It is worth emphasizing that, uniquely among the Big Five, the end Ordovician extinction was entirely limited to marine organisms, since land had yet to be colonized at that time. This was purely an oceanic apocalypse, a preview of the vulnerability of life when environmental systems collapse. The recovery was painfully slow. After the mass extinction was over, it took 50 million years for Earth's oceans to recover their former levels of diversity. 50 million years longer than the entire span from the extinction of the dinosaurs to today. Yet recover they did. The survivors of the Ordovician extinction became the ancestors of new evolutionary lineages. Coral reefs eventually returned, more spectacular than before. Fish began to evolve in earnest. And slowly, tentatively, life began its first experiments, with leaving the sea entirely. The Ordovician-Silurian extinction taught Earth's biosphere its first harsh lesson. No matter how successful, how diverse, how well-adapted life becomes, the planet itself can change the rules of the game in an instant. Ice and fire, warmth and cold, shallow seas and deep abysses, Earth systems are in constant flux, and life must either adapt or perish. This was just the beginning. Far greater challenges lay ahead, each one testing life's resilience in new and terrible ways. The next crisis would emerge from an unexpected source, the very forest that would finally colonize the land. Chapter 2. The Green Revolution's Dark Side. Fast forward 80 million years to the late Devonian period, and Earth has become a dramatically different world. The barren continents of the Ordovician have exploded with green life. For the first time in our planet's history, forests stretch across the landscape, their canopies reaching heights that would have been unimaginable in earlier eras. These aren't the familiar trees you know today. Picture forests of giant ferns towering 100 feet high, their fronds creating cathedral-like spaces beneath. Primitive trees called Archaeopteris spread their strange fern-like leaves to capture sunlight. The first seed plants are experimenting with new ways to reproduce and spread. This is evolution's great green revolution, the moment when life conquered the land. In the oceans, the success story continues. Coral reefs have rebuilt themselves into structures more magnificent than anything the Ordovician seas ever knew. Over a 30-million-year stretch, species diversity blossomed. Armored fish patrol the reefs like living tanks, some reaching lengths of 30 feet. Ammonoids, relatives of modern squid and octopus, spiral through the water with shells coiled like ram's horns. The ocean floor teems with crinoids, brachiopods, and bryozoans, creating underwater meadows of extraordinary beauty. This is the Devonian period's golden age, a time when both land and sea host unprecedented biodiversity. The planet appears to be reaching new heights of biological success. Then, slowly at first, then with accelerating devastation, something goes terribly wrong. The late Devonian extinction is unique among the Big Five in its subtlety, unfolding over many millions of years. The extinction event proceeded in a gradual manner, meaning that the rate at which species were going extinct was not much higher than it had been previously. However, the rate at which new species were emerging plummeted during the interval. This isn't the sudden catastrophe of an asteroid impact or volcanic eruption. This is a slow strangulation, a gradual suffocation of the biosphere that unfolds over millions of years. Scientists call it a press extinction, a relentless pressure that squeezes life from multiple directions until entire ecosystems collapse. The irony is devastating. The very success of life on land may have triggered its own near destruction. These traits allowed plants to get bigger and for their roots to get deeper than ever before, which would have increased the rate of rock weathering. The faster rocks weathered, the more excess nutrients flowed from land into the oceans. Here's what was happening. As forests spread across the continents, their roots penetrated deeper into the soil than any plant had ever done before. These roots broke down rocks, releasing nutrients like phosphorus and nitrogen into rivers and streams. Rain washed these nutrients into the oceans in quantities that life had never experienced. The influx would have triggered algae growth, and when these algae died, their decay removed oxygen from the oceans to form what are known as dead zones. The process is called eutrophication, and we see it happening in our modern world wherever agricultural runoff creates algal blooms. Imagine vast stretches of the ocean turning green as algae bloomed in unprecedented quantities. As these algae died and sank to the seafloor, bacteria decomposed them, consuming oxygen faster than it could be replenished. The late Devonian epoch was marked by ocean anoxia, or insufficient oxygen, a condition that may have wiped out many marine species. The dead zone spread like a plague across the ocean floors. Fish suffocated, corals bleached and died. Bottom dwelling communities that had thrived for millions of years simply vanished as oxygen levels dropped below survivable thresholds. But the forests weren't finished with their assault on the biosphere. In addition, the spread of trees would have sucked CO2 out of the atmosphere, potentially ushering in global cooling. The same process that had triggered the Ordovician extinction, atmospheric carbon dioxide removal, was happening again. But this time, the culprit wasn't mountain building, but forest growth. As trees pulled carbon dioxide from the atmosphere, global temperatures began to drop. Ice began forming at the poles. Sea levels started to fall. The shallow water ecosystems that had recovered so magnificently from the Ordovician extinction found themselves under attack once again. The extinction played out in a series of deadly pulses over 20 million years. Each pulse removed another layer of biodiversity, like peeling an onion of life. The Kellwasser events, named after specific rock layers in Germany, marked times when ocean anoxia reached crisis levels and marine ecosystems collapsed across vast regions. Despite eliminating about 70% of all marine species living just before it began, the late Devonian extinction, which occurred some 372 million years ago, was one of the least severe major mass extinctions. This speaks to the devastating nature of the other Big Five, rather than any mercy shown by the late Devonian crisis. The victims tell the story of an ecosystem in slow-motion collapse. Reef-building organisms were devastated. Many groups of brachiopods, those shell-bearing filter feeders that had dominated seafloors for hundreds of millions of years, went extinct. Trilobites, already weakened by the Ordovician extinction, suffered another devastating blow. Many coral groups vanished forever, but perhaps the most insidious aspect of the late Devonian extinction was how it changed the rules of evolution itself. To add to the puzzle, not only did some creatures go extinct during the late Devonian, but species diversification slowed down during this time. The slowdown may have been caused by the global spread of invasive species as high sea levels let creatures from previously isolated marine habitats mix and mingle, which let ecosystems around the world homogenize. For the first time in Earth's history, rising sea levels connected previously isolated ocean basins. Marine species that had evolved in isolation suddenly found themselves competing with organisms from entirely different regions. The unique local ecosystems that had driven much of the Devonian's biodiversity were homogenized into a more uniform, less diverse global ocean. The late Devonian extinction reveals a chilling truth about the relationship between life and its environment. Success itself can become a trap. The forest that represented life's greatest achievement in colonizing land also created the conditions for near-catastrophic marine extinction. The very adaptations that allowed plants to thrive, deep roots, efficient photosynthesis, rapid growth, became weapons turned against the biosphere. This extinction also shows us how interconnected Earth systems really are. Changes on land triggered cascading effects in the oceans. Atmospheric chemistry affected global climate, which in turn affected sea levels, which impacted marine ecosystems. For the first time, we see life's success in one realm creating havoc. In another, it's a preview of the environmental challenges we face today. The recovery from the late Devonian extinction set the stage for an even greater explosion of life. The devastated reefs would be rebuilt by new types of corals. The depleted seas would be repopulated by more diverse fish communities. And on land, the forest that had contributed to the crisis would evolve into even more complex ecosystems. But the lessons of the late Devonian extinction echo across deep time. Environmental change can come from unexpected sources. Success in one area can trigger failure in another, and the pace of change doesn't always determine its impact. Sometimes the slow strangulation is more devastating than the sudden blowdown as Earth's climate stabilized and life recovered from this long, slow crisis. New evolutionary experiments began. Amphibians ventured onto land. Reptiles evolved. Vast coal swamps formed from the remains of giant forests. The stage was being set for life's next great expansion and its most devastating collapse. Chapter 3. The Great Dying. If the late Devonian extinction was a slow strangulation, what happened 252 million years ago was a bullet to the head of the biosphere. The Permian mass extinction was the most extreme of any in Earth history. It's sometimes dubbed the Great Dying, with 62% of marine genera going extinct, as well as severe impacts among terrestrial biota. Perhaps only 17% of species on Earth survived it. Think about that number. 17%. That means 83% of all species on Earth. Every creature in the oceans, every plant and animal on land, vanished forever. It's the closest our biosphere has ever come to being deleted. If you could travel back in time to witness the height of the Permian-Triassic extinction, you would see a planet in the process of becoming a dead world. The Permian period had been life's greatest success story. Yet, by 260 million years ago, Earth had become a world of extraordinary diversity and complexity. Vast forests of towering tree ferns and early conifers stretched across the supercontinent Pangaea. These weren't just forests, they were coal swamps, on a scale never seen before or since, creating the vast coal deposits that powered the Industrial Revolution. In these primeval jungles lived creatures that would seem fantastical today. Sail-backed predators like Dimetrodon, with their massive dorsal fins, hunted through the undergrowth. Early relatives of mammals called therapsids had evolved sophisticated social behaviors and complex teeth. Some had even developed hair and were experimenting with warm-bloods. The oceans teemed with life. By the end of the Paleozoic, life had rebounded from the late Devonian extinction. In the sea, crinoids and their cousins the blastoids were having a heyday. Tabulate and rugose corals had made great progress in building up reefs in the late Paleozoic ocean. Brachiopods covered the seafloor in vast shell beds. Trilobites, though reduced from their Ordovician heyday, still scuttled across the ocean bottom after surviving for nearly 300 million years. Then came the event that nearly ended it all. The killer emerged from the depths of the Earth itself. In what is now Siberia, something unprecedented began to happen around 252 million years ago. The second, much larger, was in Siberia. Today we call it the Siberian Traps. The Siberian Traps represents one of the biggest eruptive episodes in Earth history. Picture volcanic eruptions so massive they defy comprehension. A volume of more than 1.5 million cubic kilometers of lava was erupted, smothering roughly 2 million square kilometers of northern Siberia. That is enough basaltic lava to bury the entire contiguous United States to a depth of half a mile. It's enough basalt to make 3 towers, each with a footprint of 1 square kilometer. That reached to the moon. But the lava was just the beginning. These weren't ordinary volcanic eruptions. The Siberian Traps vomited forth not just molten rock, but a cocktail of toxic gases that transformed Earth's atmosphere into a planetary death chamber. Carbon dioxide poured out in quantities that sent global temperatures soaring by as much as 18 degrees Fahrenheit. Sulfur dioxide created acid rain that fell across the globe. Hydrogen sulfide poisoned the air, while methane accelerated the greenhouse effect. Studies suggest that high ocean temperatures could have killed many organisms. As the planet heated up, the oceans became furnaces. Surface temperatures in tropical seas may have reached 105 degrees Fahrenheit, hot enough to kill most marine life outright. Even creatures adapted to warm water couldn't survive in what were essentially oceanic hot tubs. But heat was only one weapon in this apocalyptic arsenal. As the climate warmed and ocean circulation changed, oxygen levels in the seas plummeted. The cataclysm was the single worst event life on Earth has ever experienced. Over about 60,000 years, 96% of all marine species and about 3 of every 4 species on land died out. The oceans turned toxic. Hydrogen sulfide, that rotten egg gas, bubbled up from the deep sea, creating purple and green patches of poison that spread across vast areas. These toxic zones weren't just unlivable. They were actively deadly. Marine ecosystems collapsed. In a cascade of death, it spread from the deepest ocean basins to the shallowest coastal waters. On land, the devastation was equally complete. The world's forests were wiped out and didn't come back in force until about 10 million years later. Imagine every forest on Earth today: the Amazon, the boreal forests of Canada and Siberia, the temperate forests of North America and Europe, all dead, all gone, leaving behind only a planet of bare rock and poisoned soil. The creatures that had dominated terrestrial ecosystems for millions of years simply vanished. The magnificent sail-backed synapsids went extinct. Most of the mammal-like therapsids disappeared forever. Of the 5 mass extinctions, the Permian-Triassic is the only one that wiped out large numbers of insect species. Even insects, those champions of survival who had weathered every previous crisis, couldn't escape the Great Dying. The extinction unfolded in multiple pulses over perhaps 60,000 years, rapid in geological terms, but agonizingly slow for any creatures trying to survive it. Each pulse brought new horrors. More volcanic eruptions, more poisonous gases, higher temperatures, more toxic oceans. Life had nowhere to run, nowhere to hide. The marine ecosystem collapse was particularly devastating. Marine ecosystems took 4 to 8 million years to recover. For comparison, modern humans have existed for less than 300,000 years. The recovery from the Great Dying took more than 10 times longer than our entire species has existed. What makes the Permian-Triassic extinction so terrifying is how it demonstrates the fragility of complex ecosystems. This wasn't just a crisis that killed individual species. It was a systemic collapse that destroyed the very foundations of how life functioned on Earth. Food webs disintegrated. Nutrient cycles broke down. The chemical processes that had sustained life for hundreds of millions of years simply stopped working. The few survivors found themselves in an alien world. The exact length of the extinction event is unclear. Some scientists contend that it lasted 15 million years, while others assert that it took only tens of thousands. Regardless of the precise time frame, the survivors inherited a planet that bore little resemblance to the verdant world their ancestors had known. In the devastated oceans, only the hardiest organisms remained. Tiny mollusks called chloria lived. In vast monotonous populations, disaster species that could tolerate conditions toxic to everything else. On land, a few small reptiles and amphibians huddled in whatever refuges they could find, scratching out an existence on a planet that seemed determined to exterminate them. Yet even in this darkest hour, life's resilience began to show. The survivors weren't just lucky. They were the products of hundreds of millions of years of evolution, carrying within their genes the accumulated wisdom of countless generations. Slowly, painfully, they began to rebuild. Among the survivors was a group of reptiles that would go on to change the world. The archosaurs, ancestors of dinosaurs and crocodiles. Also surviving were the earliest mammals, tiny shrew-like creatures that would wait more than 200 million years for their chance to inherit the Earth. The Great Dying stands as the ultimate test of life's resilience. It shows us that even when the very foundations of the biosphere collapse, when the planet itself becomes hostile to life, evolution's creativity can find a way forward. But it also reveals the terrible cost of such catastrophes, the millions of years of recovery, the lost evolutionary potential, the magnificent creatures that vanish forever. As we face our own environmental crisis today, the Permian-Triassic extinction serves as both warning and hope. Warning of how quickly and completely complex ecosystems can collapse. Hope that life, even when pushed to the very brink of extinction, possesses an almost miraculous ability to endure and rebuild. The world that emerged from the Great Dying was fundamentally different from what came before. New types of corals built new kinds of reefs. New predators and prey evolved new strategies for survival. And in this transformed world, A group of reptiles began evolutionary experiments that would lead to some of the most magnificent creatures ever to walk the Earth. Chapter 4. When giants ruled the world in the aftermath of the Great Dying, Earth resembled a blank canvas waiting for new masterpieces to be painted. The Triassic period, beginning 252 million years ago, represents one of evolution's most remarkable comeback stories. From the ashes of the worst extinction in Earth's history, life not only recovered, it invented entirely new ways to dominate the planet. The early Triassic world was alien and harsh. Vast deserts stretched across the supercontinent Pangaea, broken only by seasonal monsoons that turned dry riverbeds into raging torrents. The extinction of other vertebrate species on land allowed dinosaurs to flourish. But dinosaurs hadn't arrived yet. First, other reptiles would experiment with gigantism and dominance in the recovering oceans. New reef ecosystems began to form, built by previously unknown types of corals called scleractinians, the ancestors of all modern coral reefs. These weren't rebuilding the old Permian reefs. They were creating something entirely new. New types of marine reptiles began experimenting with aquatic life. Ichthyosaurs, reptiles that looked like dolphins, started their evolutionary journey toward becoming some of the ocean's most efficient predators. On land, the surviving reptiles diversified rapidly into ecological niches left vacant by the Phytus. Great Dying. Among them were the archosaurs, a group that would eventually give rise to crocodiles, pterosaurs, and dinosaurs. But in the Triassic, their experiments took different forms. Picture Desmatosaurus, a 15-foot-long armored archosaur that looked like a massive crocodile covered in bony plates. These weren't aquatic hunters, but terrestrial herbivores, using their powerful limbs to dig up roots and their formidable armor to defend against predators. Alongside them lived Pastosuchus, a 20-foot-long predator that walked on its hind legs like a giant crocodile that had learned to stand upright. Therapsids flourished in the Triassic, now that their synapsid competitors had been suffocated. These crocodilian relatives were attended by the first dinosaurs, but dinosaurs were the sideshow rather than the main act. This is crucial to understand. In the Triassic world, dinosaurs were not the dominant land animals. They were small, relatively rare creatures living in the shadows of much larger archosaurs. The first dinosaurs were modest creatures, rarely larger than a modern dog. Aeropter, one of the earliest known dinosaurs, was only 3 feet long and weighed about 20 pounds. Ararosaurus, among the largest early dinosaurs, reached only 20 feet in length, impressive, but dwarfed by the giant archosaurs that ruled the Triassic landscape. Yet these early dinosaurs possessed something special, an improved hip structure that made them more efficient runners, and in many cases, they had developed sophisticated social behaviors and possibly even warm-bloodedness. They were evolution's experiments in efficiency, preparing for a future they couldn't yet claim. For 50 million years, this diverse Triassic world flourished. The climate was generally warm and humid, with no ice caps at the poles. Vast forests of conifers, ferns, and cycads supported complex food webs. In the oceans, marine ecosystems rebuilt themselves with spectacular success, creating new types of reefs and supporting new forms of marine life. Then, around 201 million years ago, disaster struck again, although it remains unclear exactly why. This fourth mass extinction occurred. Scientists think that massive volcanic activity occurred in an area of the world now covered by the Atlantic Ocean. The breakup of Pangaea had begun, and as the supercontinent split apart, it unleashed volcanic forces that rivaled even the Siberian traps. The Central Atlantic Magmatic Province, or CAMP, began erupting along what would become the Atlantic Ocean. This massive slug of basalt was intruded into the Newark Basin during The breakup of Pangaea. Picture volcanic eruptions stretching for thousands of miles as the Earth's crust literally tore apart. Lava flows covered vast areas of what would become eastern North America, Western Africa, and South America. Similar to the Permian extinction, volcanoes released enormous amounts of carbon dioxide, driving climate change and devastating life. On Earth, global temperatures increased, ice melted, and sea levels rose and acidified. The pattern was becoming familiar. Massive volcanism leading to greenhouse gas release, global warming, ocean acidification, and mass extinction. But the Triassic-Jurassic extinction had its own unique characteristics. 4 of the Big 5 extinctions were at least partly the result of climate change in the form of global warming and Permian, and Triassic, or cooling and/or division, late Devonian. The end Triassic warming was particularly severe, with ocean temperatures rising to lethal levels and atmospheric carbon dioxide reaching concentrations 4 times higher than today. In the sea, about half of the Triassic genera didn't make it into the Jurassic. Almost every kind of ammonoid and bivalve was decimated. The marine ecosystems that had so painstakingly rebuilt themselves after the Great Dying faced another catastrophic collapse. Coral reefs suffered massive bleaching events. Many types of marine reptiles went extinct. As a result, many marine and land species became extinct. These included large prehistoric crocodiles and some flying pterosaurs. On land, the great archosaurs that had dominated Triassic ecosystems for 50 million years suddenly found themselves unable to cope with the rapidly changing climate. This is where the story takes a dramatic turn. Only after the end Triassic extinction could the dinosaurs surge forward and dominate the Mesozoic land surface. But first, their crocodilian overlords must be cleared away. The Triassic-Jurassic extinction demonstrates one of evolution's most important principles. Catastrophes don't just destroy, they create opportunities. The extinction that ended the Triassic period wasn't just the death of one world. It was the birth of another. A world where dinosaurs would grow to unprecedented sizes, where pterosaurs would master the skies, and where marine reptiles would become the ocean's apex predators. This extinction also reveals how environmental change can completely reshape the hierarchy of life. The archosaurs that had seemed so dominant, so well adapted to Triassic conditions, proved vulnerable when those conditions changed rapidly. Meanwhile, the small, seemingly insignificant dinosaurs possessed exactly the traits needed to thrive in the post-extinction world. The Triassic-Jurassic extinction reminds us that in the lottery of survival, size and current dominance don't guarantee a ticket to the future. Sometimes, the meek really do inherit the Earth, or at least get their chance to reshape it entirely. As the volcanic fires of the Central Atlantic magmatic province finally cooled and the climate stabilized, the survivors found themselves in a world of unprecedented opportunity. The age of dinosaur dominance was about to begin, leading to some of the most spectacular creatures in Earth's history. But even these magnificent giants would eventually face their own appointment with extinction. Chapter 5. The day the Earth stood still. It's 66 million years ago, and Earth is experiencing a golden age unlike anything before or since. The Cretaceous period represents the pinnacle of dinosaur evolution and diversity. Tyrannosaurus rex stalks through dense forests, its 7-inch teeth capable of crushing cars. Massive herds of Triceratops thunder across vast plains, their elaborate frilled heads serving as both shield and display. In the skies above, pterosaurs with wingspans of 35 feet soar like living aircraft. This is not the swampy, primitive world often portrayed in popular culture. The late Cretaceous Earth is warm, lush, and incredibly diverse. Sea levels are 600 feet higher than today, creating vast shallow seas that teem with life. Flowering plants, angiosperms, have recently evolved and are transforming terrestrial ecosystems. The first grasses are beginning to spread. Early mammals scurry through the underbrush. Still small but beginning to diversify. In the oceans, marine reptiles have reached sizes that dwarf modern whales. Mosasaurs, massive marine lizards, patrol the seas like swimming dragons, some reaching lengths of 60 feet. Plesiosaurs with necks longer than their bodies glide through the water. Ammonites spiral through the waves in shells that can measure 6 feet across. The diversity is staggering. There are more species of dinosaurs alive in the late Cretaceous than there are species of mammals today. From tiny feathered predators to gigantic long-necked sauropods measuring over 100 feet long, dinosaurs have filled every conceivable ecological niche. They are the unquestioned masters of the terrestrial realm. But in space, 66 million miles away, a chunk of rock and metal is hurtling toward Earth at 45,000 miles per hour. It's about 6 miles wide, roughly the size of Mount Everest. In a few hours, it will end the age of dinosaurs and reshape the future of life on Earth. The asteroid, though some scientists prefer the term impactor, since its exact composition remains debated, approaches from the southeast. Perhaps the most famous of the major mass extinctions is the Cretaceous-Paleogene, or KPG extinction, which occurred some 66 million years ago. The overwhelming scientific consensus holds that the impact of a giant extraterrestrial object was the primary cause of the extinction. At 11:47 a.m. local time, give or take a few minutes, the impactor slams into what is now the Yucatan Peninsula in Mexico at a shallow angle. The energy released is equivalent to 10 billion Hiroshima bombs, exploding simultaneously. The main evidence of this event is an enormous impact crater found near the Yucatan Peninsula in northeastern Central America. The Chicxulub crater, as it's now known, measures 110 miles across and 12 miles deep. But the crater itself is just the beginning of the story. The impact triggers a cascade of catastrophes that will reshape the entire planet in a matter of hours. The first seconds after impact are almost incomprehensible. The asteroid vaporizes instantly, along with the surrounding bedrock. A fireball hotter than the surface of the sun expands outward at supersonic speeds. An impact fragment with an estimated diameter of 10 kilometers, or 6.2 miles, struck Earth, sending huge waves of heat, dust, and soot around the planet. Massive tsunamis race outward from the impact site. These aren't the 100-foot waves we might see from submarine earthquakes today. These are walls of water over a mile high, traveling at 450 miles per hour. They devastate coastlines thousands of miles away, penetrating hundreds of miles inland and scouring everything in their path. But the immediate destruction around the impact site is just a local catastrophe. The global effects begin within minutes. Trillions of tons of vaporized rock and debris are hurled into the atmosphere and beyond. Some of this material reaches escape velocity and actually leaves Earth entirely. Chunks of our planet, complete with potentially fossilized microbes, scatter across the solar system. Most of the debris, however, falls back to Earth as a hellish rain of molten droplets. The airborne soot blocks sunlight, forcing ecosystems to collapse. As this material re-enters the atmosphere, it heats up through friction, creating a global firestorm. The entire planet becomes an oven. Imagine standing anywhere on Earth during the hours after impact. First, you'd see what looks like a second sun rising in the sky as the impact fireball becomes visible. Then, the sky would begin to glow as countless tiny meteors, pieces of Earth itself, streak back down through the atmosphere. The air temperature would rise to over 300 degrees Fahrenheit, hot enough to ignite vegetation worldwide. Forests that had grown for millions of years burst into flames simultaneously across the globe. The Amazon rainforest, the boreal forests of the Arctic, the temperate woodlands all burning at once, creating smoke plumes that darken the sky. Any animal larger than a house cat caught in the open would be cooked alive. Then comes the darkness. The dust, ash, and smoke from global wildfires block out the sun for months. It's not just dim, it's darker than the darkest night. Photosynthesis stops. Plants die. The food web collapses from the bottom up. The darkness is only the beginning of the environmental chaos. Sulfur compounds from the vaporized rock create acid rain that falls for years. The pH of the oceans drops rapidly, dissolving the shells of countless marine organisms. Without sunlight, global temperatures plummet, creating an impact winter that can last for years. The numbers tell the story of devastation. It marked the end of about 67% of all species living immediately beforehand, including the non-avian dinosaurs. Around 65 million years ago, something unusual happened on our planet. We can see it in the fossil record. Fossils that are abundant in earlier rock layers are simply not present in later rock layers. But the extinction wasn't random. Size mattered enormously. Any land animal larger than about 50 pounds had virtually no chance of survival. This size cutoff is why birds, technically dinosaurs themselves, survived while their larger cousins perished. Small mammals, crocodiles, turtles, and many fish survived, but virtually all large land animals disappeared forever. The marine extinction was equally devastating. The magnificent ammonites that had ruled the seas for 300 million years vanished entirely. Large marine reptiles like mosasaurs and plesiosaurs died out. Many types of marine plankton, the base of oceanic food webs, went extinct, causing ecosystem collapse throughout the water column. The extinction event's selectivity reveals something crucial about survival during catastrophes. It wasn't about being the strongest or the most dominant. It was about having the right traits for a changed world. Small body size, the ability to shelter underground or underwater, and diets that didn't depend on fresh vegetation became the keys to survival. As a result, mammals and birds, avian dinosaurs, were able to gain dominance on land. In the aftermath of the extinction, the survivors found themselves in a world of unprecedented opportunity. With the giant dinosaurs gone, ecological niches that had been closed for 135 million years suddenly opened up. Early mammals, which had spent the entire Mesozoic era as small, nocturnal creatures, began experimenting with larger body sizes and new lifestyles. Some became herbivores, filling the niches left by giant dinosaurs. Others became large predators. Within just a few million years, mammals had diversified into forms that would eventually lead to elephants, whales, bats, and primates. The extinction that occurred 65 million years ago wiped out some 50% of plants and animals. But it also made possible the world we know today. Without the KPG extinction, mammals might never have evolved beyond small, shrew-like creatures. There would be no elephants, no whales, no humans. The asteroid that killed the dinosaurs also made our existence possible. The Cretaceous-Paleogene extinction stands as perhaps the most dramatic example of how a single event can completely alter the trajectory of life on Earth. It demonstrates the awesome power of cosmic forces and the random nature of catastrophic change. The dinosaurs weren't failing as a group. They were thriving right up until the moment of impact. This extinction also reveals something profound about the nature of dominance in Earth's ecosystems. For 135 million years, dinosaurs had been the undisputed rulers of terrestrial life. They had survived climate changes, sea level fluctuations, and volcanic episodes that would devastate modern ecosystems. Yet a single asteroid, lasting perhaps a few seconds, ended their reign permanently. The KPG extinction serves as both an ending and a beginning. It closed the book on the Mesozoic era, the age of reptiles, and opened the Cenozoic era, the age of mammals. It reminds us that life's history is punctuated by moments of profound change, when the established order gives way to new possibilities. Today, as we search the skies for potentially hazardous asteroids and develop plans to deflect them, the KPG extinction provides both warning and hope. Warning that cosmic catastrophes can end even the most successful evolutionary experiments. Hope that life, given time, can recover from even the most devastating setbacks and create new forms of beauty and complexity. The age of dinosaur dominance was over, but the story of life on Earth was far from finished. In fact, it was about to enter a new chapter that would eventually lead to the most dangerous and creative species the planet had ever produced. Chapter 6. The Rise of the Mammalian Empire in the immediate aftermath of the asteroid impact. Earth resembled a post-apocalyptic wasteland. Beneath the perpetual twilight of dust-darkened skies, a few small, furry creatures emerged from underground burrows and hollow logs. These were the mammalian survivors, tiny, shrew-like animals that had scavenged in the shadows of dinosaurs for over 100 million years. Suddenly, they found themselves the inheritors of a devastated but opportunity-rich planet, the early Paleocene. World, beginning 66 million years ago, was a strange and empty place. Vast forests had been reduced to ash. Many river systems had been disrupted by debris flows. The towering ecosystems built around giant dinosaurs had collapsed, leaving behind simplified communities of survivors. But for the mammals that had survived the KPG extinction, this devastation represented the greatest evolutionary opportunity in Earth's history. These early survivors were not the impressive creatures that mammals would become. The largest was about the size of a small dog. Most were mouse-sized insectivores that could survive on beetles, worms, and plant matter. They possessed several crucial adaptations that had allowed them to survive the extinction. Small body size, the ability to shelter underground, relatively low metabolic requirements, and the capacity to survive on whatever food was available. Within just a few 100,000 years, an evolutionary instant, these modest survivors began one of the most dramatic adaptive radiations in Earth's history. Without giant dinosaurs to compete with or hide from, mammals began experimenting with body sizes and lifestyles that had been impossible during the Mesozoic. The first experiments were modest but revolutionary. Some early mammals began eating more plant matter, developing specialized teeth for grinding leaves and stems. Others became more effective predators, evolving sharper claws and teeth. Still others took to the trees, developing improved climbing abilities and better grasping hands. By 10 million years after the extinction, mammals had already diversified into forms that would be recognizable today. They were early primates, swinging through the recovering forests. Primitive ungulates, ancestors of horses and cows, grazed in expanding grasslands. Early carnivores hunted in packs. Some mammals had even returned to the water, beginning the evolutionary journey that would eventually produce whales. But the most dramatic changes were still to come. As the climate warmed during the Paleocene-Eocene thermal maximum around 56 million years ago, mammalian evolution accelerated even further. This period of global warming created vast tropical forests that stretched from pole to pole, providing new habitats and opportunities for mammalian diversification. During this greenhouse Earth phase, mammals achieved sizes that rivaled the dinosaurs they had replaced. Eutherium, a massive herbivore with bizarre horns and tusks, reached the size of a modern rhinoceros. Early relatives of elephants appeared. Giant ground sloths evolved in South America. Some mammals even experimented with returning to aquatic environments, the ancestors of whales. began their remarkable transition from land-dwelling carnivores to ocean giants. The diversification wasn't limited to land. Bats evolved powered flight, becoming the first mammals to master the air since pterosaurs disappeared. Early whales like Ambulocetus, literally walking whale, lived amphibious lifestyles, hunting both on land and in shallow seas. Within 15 million years of the KPG extinction, some whales had become fully aquatic and reached enormous sizes. This mammalian radiation demonstrates evolution's remarkable creativity when ecological constraints are suddenly removed. For over 100 million years, mammalian evolution had been constrained by the presence of dinosaurs. Mammals remained small, nocturnal, and ecologically limited. But given the opportunity, they rapidly filled every available niche and invented new ones. The transformation of Earth's ecosystems during the Paleogene was as dramatic as anything in the planet's history. Grasslands expanded across continents, co-evolving with grazing mammals. Tropical forests reached unprecedented diversity. Ocean ecosystems rebuilt themselves around new types of marine life. Within 20 million years of the extinction, mammalian ecosystems had achieved a complexity that matched or exceeded anything from the Mesozoic era. Yet even as mammals diversified and thrived, they faced their own evolutionary challenges. Climate change continued to shape the planet. Around 34 million years ago, global temperatures began to cool. Ice sheets formed at the poles, and the lush greenhouse world of the early Paleogene gave way to more seasonal, temperate climates. These climate changes triggered their own evolutionary responses. Mammals adapted to cooler, drier conditions by evolving more efficient locomotion, better insulation, and new feeding strategies. Grasses co-evolved with grazing mammals, creating the vast savannas that would eventually become the backdrop for human evolution. The mammalian success story continued through the Miocene epoch, 23 to 5 million years ago, when mammalian diversity reached its peak. Vast herds of different species roamed the continents. Predators evolved sophisticated hunting strategies. Early apes began experimenting with upright walking. The mammalian empire that had emerged from the KPG extinction had become the most successful group of large land animals in Earth's history. But success, as we've seen repeatedly in Earth's history, can create its own vulnerabilities. As mammals grew larger and more specialized, they became increasingly dependent on stable ecosystems and predictable food sources. They were setting themselves up for their own encounters with mass extinction. Starting around 50,000 years ago, a new pattern of extinction began to emerge. Large mammals' megafauna started disappearing at unprecedented rates. Giant ground sloths vanished from South America. Massive cave bears disappeared from Europe. Woolly mammoths and saber-toothed cats went extinct across North America. Australia lost its giant marsupials. This wasn't a single extinction event like the KPG impact, but rather a rolling wave of extinctions that followed a specific pattern. Wherever a particular species of mammal appeared, large mammals soon disappeared. Large mammals are at greater risk. For example, giant sloths, mastodons, and saber-toothed tigers became extinct only about 10,000 years ago. They just couldn't find a way to outmuscle nature. The mammal causing these extinctions wasn't particularly large or physically imposing. It weighed less than 200 pounds and lacked impressive claws, teeth, or armor. But it possessed something that made it more dangerous than any predator in Earth's history: intelligence, technology, and the ability to cooperate in large groups. Homo sapiens had arrived on the scene, and the age of human-driven extinction was beginning. The mammalian empire that had ruled for 65 million years was about to face its greatest challenge yet, not from asteroids or volcanoes, but from one of its own members. The story of mammalian success following the KPG extinction reveals evolution's incredible adaptability and creativity. It shows how catastrophic destruction can become the foundation for new forms of life and complexity. The small, unremarkable mammals that survived the asteroid impact became the ancestors of elephants, whales, bats, and humans, a diversity, a form and function that rivals anything in Earth's history. Yet this same story warns us about the fragility of even the most successful evolutionary experiments. The mammalian megafauna that dominated the Thames, Pleistocene creatures that had survived ice ages and climate changes, proved vulnerable to a new type of extinction pressure: intelligent, tool-using predators with global reach. As we trace the rise of mammals from the ashes of the dinosaur extinction to their dominance of modern ecosystems, we see both the resilience and vulnerability of life. Success creates opportunities, but also dependencies. Dominance can last for millions of years, but can end surprisingly quickly when conditions change. The mammalian radiation following the KPG extinction set the stage for the next chapter in our story: the emergence of a species that would not only survive extinction events, but potentially cause them. For the first time in Earth's history, a single species would develop the power to trigger a mass extinction through its own actions, rather than through cosmic accident or geological catastrophe. The age of human-driven extinction was about to begin, and with it, questions that no previous mass extinction had ever raised. Can an intelligent species recognize the destruction it's causing? Can it change course in time? And what happens when the extinction agent is also the only species capable of preventing the extinction? Chapter 7. The sixth extinction begins for 66 million years after the asteroid impact. Earth's ecosystems rebuilt themselves into new forms of complexity and beauty. Mammals diversified into thousands of species. Birds, the surviving dinosaurs, mastered virtually every environment from deep ocean to high atmosphere. Plants and insects co-evolved into relationships of stunning intricacy. By 100,000 years ago, Earth hosted levels of biodiversity that may have been the highest in the planet's history. Then, in what amounts to less than a single tick of the geological clock, everything began to change. The agent of change was unremarkable by the standards of previous mass extinctions. No asteroid plummeted from space. No supervolcanoes erupted. No ice sheets advanced across the continents. Instead, a single species of African primate began to spread across the globe. And wherever it went, other species started disappearing. Homo sapiens evolved around 300,000 years ago in Africa. But for most of our existence, we were just another large mammal competing for resources in complex ecosystems. Our early ancestors lived in small bands, hunted with primitive tools, and had little more impact on their environment than other predators of similar size. But around 70,000 years ago, something changed. Whether through genetic mutations that enhanced our cognitive abilities, cultural innovations that allowed better cooperation, or simply reaching a critical population threshold, humans began to demonstrate an unprecedented capacity for environmental modification. The pattern that emerged was unlike anything in Earth's history. As humans spread from Africa into the Middle East, Asia, Australia, and eventually the Americas, they left behind a trail of extinctions that followed their migration routes with eerie precision. This wasn't coincidence, it was cause and effect. On a global scale, Australia provides a particularly clear example. When humans first arrived around 50,000 years ago, the continent hosted an extraordinary array of megafauna. Diprotodon, a giant wombat the size of a small car, grazed in herds. Across the interior, Mammalian, a monitor lizard 23 feet long, was perhaps the largest terrestrial predator since T-Rex. Giant kangaroos stood 10 feet tall. Marsupial lions prowled the forests. Within a few thousand years of human arrival, over 85% of Australia's large mammal species were extinct. The pattern was repeated as humans reached other continents. When people first crossed the Bering Land Bridge into North America around 15,000 years ago, the continent teemed with giants. Woolly mammoths, giant ground sloths, cave bears, saber-toothed cats, and short-faced bears dominated the landscape. By 10,000 years ago, most of these magnificent creatures had vanished. Never before has a single species been responsible for such destruction on Earth. The extinctions weren't gradual or spread over millions of years. They happened within centuries or millennia of human contact. What made humans so uniquely destructive? Unlike previous extinction agents, asteroids, volcanoes, climate change, humans were intelligent, adaptable, and capable of rapid cultural evolution. We developed increasingly sophisticated tools, hunting strategies, and social organizations. We learned to use fire as a landscape management tool, fundamentally altering ecosystems across entire continents. But the early human extinctions were just the beginning. Around 10,000 years ago, humans made another revolutionary change that would accelerate our impact exponentially. We invented agriculture. Agriculture allowed human populations to grow far beyond what hunting and gathering could support. It also required massive landscape modifications. Forests were cleared for crops. Wetlands were drained. Grasslands were converted to farmland. Wild ecosystems were replaced with simplified agricultural systems designed to support a single species. Currently, 40% of all land has been converted for food production. Agriculture is also responsible for 90% of global deforestation and accounts for 70% of the planet's freshwater use, devastating the species that inhabit those places by significantly altering their habitats. As human populations grew and technology advanced, our impact accelerated. The Industrial Revolution, beginning in the 1760s, marked another inflection point. Suddenly, humans could extract resources, modify landscapes, and produce waste at scales that rivaled geological processes. Steam engines allowed us to mine coal and metal from previously inaccessible deposits. Railways and ships enabled us to transport resources and species across continents and oceans. Chemical industries began producing synthetic compounds that had never existed in nature. We were becoming what scientists now call a geological force, a single species capable of altering the planet's fundamental systems. The scale of modern human impact is difficult to comprehend. We have moved more earth and rock through mining than all the world's rivers carry to the ocean. We have created new compounds that will persist in Earth's geological record for millions of years. We have altered the composition of the atmosphere, changing the global climate. We have modified over 75% of the land surface and over 40% of the marine environment. The result is what many scientists are calling the sixth mass extinction. The Holocene extinction, also referred to as the Anthropocene extinction or the sixth mass extinction, is an ongoing extinction event caused exclusively by human activities during the Holocene epoch. Current extinction rates are estimated at 100 to 1,000 times higher than natural background extinction rates and are accelerating. The current rate of extinction is between 100 and 1,000 times higher than the pre-human background rate of extinction, which is jaw-dropping. We are definitely going through a sixth mass extinction. But this extinction is different from the previous 5 in crucial ways. Unlike previous extinction events caused by natural phenomena, the sixth mass extinction is driven by human activity, primarily, though not limited to, the unsustainable use of land, water and energy use, and climate change. The mechanisms are diverse and interconnected. Habitat destruction remains the primary driver. We have fragmented natural ecosystems into small, isolated patches that cannot support viable populations of many species. Pollution poisoning air, water, and soil affects everything from insects to marine mammals. Climate change is altering temperature and precipitation patterns faster than many species can adapt. Invasive species, often introduced by human activities, are disrupting ecosystems worldwide. Overexploitation through hunting, fishing, and harvesting has pushed many species beyond sustainable limits. These are just some of the devastating changes caused by humans. The numbers are staggering. According to the UNDP's 2020 Human Development Report, The Next Frontier, Human Development and the Anthropocene, the planet's biodiversity is plunging, with a quarter of species facing extinction, many within decades. The 2022 Living Planet Report found that vertebrate wildlife populations have plummeted by an average of almost 70% since 1970, with agriculture and fishing being the primary drivers of this decline. In the last 500 years, since the time of European exploration and colonization of the Americas and Caribbean by Columbus and others, humans have been responsible for documenting the extinction of over 800 species. Nearly 17,000 more are known to be threatened with extinction. Examples of recent human-caused extinctions include the dodo, golden toad, great auk, passenger pigeon, Pyrenees ibex, St. Helena olive, Steller sea cow, Tasmanian tiger, and Yangtze River dolphin. What makes the current extinction crisis particularly alarming is its speed and scope. Mass extinctions are characterized by the loss of at least 75% of species within a geologically short period of time, i.e., less than 2 million years. While we haven't reached that threshold yet, if current trends continue, we could reach mass extinction levels within centuries rather than millions of years. The interconnected nature of modern ecosystems means that extinctions can trigger cascading effects. All life on Earth is finely interwoven. This delicate balance has been established over millions of years. As one species becomes extinct, many other species are affected, putting a number of ecosystems in danger of collapsing. The sixth extinction also threatens ecosystem services that humans depend on for survival. Pollination, water purification, climate regulation, pest control, soil formation, and nutrient cycling all depend on biodiversity. As species disappear, these services become impaired, potentially threatening human civilization itself. Unlike previous mass extinctions, this one comes with an unprecedented element: awareness. For the first time in Earth's history, the species causing a mass extinction is also capable of understanding what it's doing and potentially stopping it. We are currently in the beginning stages of the so-called sixth mass extinction, with rates of species loss that are frighteningly high, even when compared with the highest rates measured in the fossil record over the last 500 million years. This awareness brings both hope and responsibility. We understand the mechanisms driving the extinction crisis. We know what needs to be done to address it: reduce habitat destruction, control pollution, manage climate change, regulate invasive species, and end overexploitation. The question is whether we have the collective will to act on this knowledge. Some conservation successes show that recovery is possible when we make the effort. Species like the California condor, black-footed ferret, and Arabian oryx have been brought back from the brink of extinction through intensive conservation efforts. Protected areas, breeding programs, and international treaties have helped slow the extinction rate for some groups, but these successes are exceptions in a larger pattern of decline. Despite this grim outlook, there are efforts to mitigate biodiversity loss. Conservation initiatives, international treaties, and sustainable practices aim to address this crisis. However, these efforts do not counteract the fact that human activity still threatens to cause large amounts of damage to the biosphere, including potentially to the human species itself. The sixth extinction presents us with a unique moment in Earth's history. Unlike previous mass extinctions that were imposed on life by external forces, this one is being caused by life itself, specifically by us. This means we have the power to influence its outcome in ways that the victims of previous extinctions never could. The story of the sixth extinction is still being written. Its ending depends on choices we make in the coming decades about how we relate to the natural world and whether we can learn to live within Earth's ecological limits. We stand at a crossroads that no species has ever faced before. The power to destroy or preserve the magnificent biological heritage that 4 billion years of evolution has created. Chapter 8. Racing against time. To understand the true magnitude of the sixth extinction, we need to grasp something that seems simple, but is actually profound: the speed at which it's happening. Throughout Earth's history, the pace of extinction has been one of the key factors determining whether life could recover and rebuild. Today, we're conducting a real-time experiment in how fast a biosphere can be dismantled. The numbers behind modern extinction rates are staggering in their implications. Scientists estimate that at least 99.9% of all species of plants and animals that ever lived are now extinct. This might sound alarming, but it's actually normal. Extinction has always been part of evolution. What's not normal is the rate at which it's happening now. Under natural conditions, extinction occurs at what scientists call the background rate, a natural baseline of species loss that has prevailed over millions of years. Earth's normal extinction rate is often thought to be somewhere between 0.1 and 1 species per 10,000 species per 100 years. This is known as the background rate of extinction. To put this in perspective, if you had 10,000 species in a region, you would naturally expect to lose about 1 species per century. This slow, steady rate of loss was balanced by the evolution of new species, maintaining overall biodiversity over geological timescales. Today's extinction rates are not just above the background rate, they're catastrophically higher. Current extinction rates are estimated at 100 to 1,000 times higher than natural background extinction rates and are accelerating. Some estimates suggest the rate could be even higher, up to 10,000 times the background rate for certain groups of organisms. What does this mean in practical terms? Instead of losing 1 species per 10,000 per century, we might be losing 100 to 1,000 species per 10,000 per century. The difference between these rates is the difference between a gentle rain and a hurricane. But raw extinction rates only tell part of the story. The most revealing pattern is what scientists call the Anthropocene acceleration, the dramatic speeding up of extinction rates in recent decades. The number of vertebrate species recorded as extinct since year 1500 is 338, or 667 if we count species extinct in the wild and those regarded as threatened. These numbers might seem small compared to estimates of millions of species on Earth, but they result from close to 60% and 70%, respectively, occurring over just the last 120 years. This acceleration pattern reveals something crucial: the extinction crisis isn't just a gradual increase over historical baselines. It's an exponential curve that's becoming steeper with each passing decade. The rate of species loss has doubled since 1970. What took centuries in the past now happens in decades. What took decades now happens in years. Even more alarming is that these documented extinctions represent only the tip of the iceberg. Many of these extinctions are undocumented, as the species are often undiscovered before their extinctions. Scientists estimate that we've only cataloged about 20% of the species that actually exist on Earth. We're losing species we never even knew existed. The Living Planet Index, which tracks populations of vertebrate species worldwide, shows a 69% average decline since 1970. This doesn't mean 69% of species have gone extinct, but rather that the average population size has dropped by more than 2/3 in just 50 years. For many species, these population crashes are stepping stones to extinction. Regional patterns reveal even more dramatic losses. In tropical regions, which host the majority of Earth's biodiversity, extinction rates are particularly high. The Amazon rainforest alone may be losing 100 species per day, though many of these losses go unrecorded. Island ecosystems, which often host unique species found nowhere else, have experienced some of the highest extinction rates of all. The pace of extinction varies dramatically among different groups of organisms, revealing the complex ways human activities affect different parts of the biosphere. Amphibians are experiencing what scientists call an extinction crisis, rates of loss far above even the elevated baseline of the sixth extinction. Over 40% of amphibian species are threatened with extinction, and many populations have crashed by 90% or more in just a few decades. Large mammals face particularly high extinction risks. Of the 5 mass extinctions, the Permian-Triassic is the only one that wiped out large numbers of insect species. The current extinction crisis is different. It's affecting large animals disproportionately. Just as human activities tend to disrupt the top of food webs, marine ecosystems are experiencing their own acceleration of loss. Coral reefs, often called the rainforests of the sea, are undergoing back-to-back bleaching events that are killing entire reef systems. Fish populations have declined by an average of 49% since the 1970s. Large marine animals like sharks, tuna, and marine mammals have experienced particularly steep declines. The speed of modern extinction creates cascading effects that amplify the crisis. In stable ecosystems, the loss of one species can often be compensated by related species that expand into the vacant niche. But when multiple species disappear rapidly, these compensatory mechanisms break down. Entire ecological networks can collapse in a matter of years rather than millennia. Pollinator decline provides a particularly clear example of how extinction speed affects ecosystem function. Bees, butterflies, and other pollinators are disappearing so rapidly that many plant species can't find replacement pollinators fast enough. This creates feedback loops where plant extinctions accelerate pollinator extinctions, which accelerate more plant extinctions. Climate change is adding another layer of speed to the extinction crisis. As global temperatures rise and precipitation patterns shift, species must either adapt, migrate, or go extinct. The problem is that current climate change is happening 10 to 100 times faster than past natural climate changes. Many species simply cannot adapt or migrate quickly enough to keep up. The concept of extinction debt reveals how the speed of modern environmental change creates delayed but inevitable extinctions. When habitats are destroyed or fragmented, some species can persist for decades in remnant populations that are too small to be viable long-term. These are the living dead species that are functionally extinct but haven't died out yet. The faster we modify environments, the more extinction debt we accumulate. Technology has allowed us to document this acceleration in real time. Satellite imagery shows deforestation happening so rapidly that we can watch rainforests disappear between successive photographs. Underwater cameras reveal coral bleaching events unfolding over weeks rather than years. GPS tracking shows animal populations crashing in real time as their habitats are destroyed. Perhaps most disturbing is the evidence that the acceleration is still increasing. Calculations also suggest that although we may not be there yet, if rates increase to the point at which all threatened species became extinct within the century, we would reach a sixth mass extinction event with a magnitude comparable to past. mass extinctions within approximately 240 to 540 years. This timeline is unprecedented in Earth's history. Previous mass extinctions unfolded over hundreds of thousands to millions of years. We're potentially creating a mass extinction in centuries, a pace of destruction that gives ecosystems no time to adapt, evolve, or migrate. The speed of the sixth extinction also creates unprecedented challenges for conservation. Traditional conservation strategies were designed for relatively stable threats and gradual changes. But when species can go from abundant to extinct in a few decades, conservation must become much more rapid and proactive. Emergency interventions, like captive breeding, habitat restoration, and species reintroductions must happen on timescales that match the speed of destruction. This requires resources, coordination, and political will at scales that humanity has never previously mobilized for conservation. Yet the speed of the crisis also creates opportunities. Unlike previous mass extinctions, we can see this one coming. We have scientific tools to predict which species are most at risk. We can model how different conservation strategies might affect outcomes. We have communication technologies that allow global coordination of conservation efforts. The question is whether human society can respond quickly enough to match the pace of the crisis we've created. Can we develop sustainable technologies, change economic systems, and alter consumption patterns faster than we're destroying ecosystems? Can we scale up conservation efforts to match the scale of destruction? Time is the critical factor in the sixth extinction. Every year of delay means more species cross the threshold from viable populations to extinction debt to disappearance. Every decade of inaction closes off more options for recovery. The window for preventing a full mass extinction may be measured in decades rather than centuries. Understanding the speed of the current extinction crisis helps us appreciate both its uniqueness and its urgency. We're not just witnessing another mass extinction. We're witnessing the fastest destruction of biodiversity in Earth's history, happening in a single human lifetime rather than geological ages. Chapter 9. The Domino Effect. The passenger pigeon once darkened North American skies in flocks so massive that they took days to pass overhead. At their peak, there may have been 3 to 5 billion passenger pigeons, perhaps 25% of all birds in North America. They were so numerous that people assumed they could never disappear. In 1914, the last passenger pigeon died in the Cincinnati Zoo, and with her death, we learned a crucial lesson about how ecosystems function. Even the most abundant species can vanish, and when they do, they take entire networks of life with them. The passenger pigeon's extinction created what ecologists now call a cascade effect, the disappearance of one species triggering the decline or extinction of many others. White-footed mice, the primary carriers of Lyme disease, used to compete with passenger pigeons for foods, like acorns. With the pigeons gone and predators like wolves and cougars on the decline, mouse populations have boomed, and with them, human cases of Lyme disease. This example involves the disappearance of just one genus. A mass extinction of genera could mean a proportional explosion of disasters for humanity. The passenger pigeon story reveals a fundamental truth about the sixth extinction. It's not just about losing individual species, it's about the unraveling of the complex web of relationships that hold ecosystems together. Every species exists within networks of interdependence, so complex that even ecologists are still discovering their full extent. Plants depend on pollinators, which depend on flowering plants. Predators control herbivore populations, which affects plant communities, which determines soil chemistry, which influences which plants can grow. Decomposers break down dead material, releasing nutrients that feed new life. Remove key players from these networks, and the entire system can collapse. Modern ecosystem science has revealed that biodiversity isn't just about having many species. It's about having the right species in the right relationships. Some species act as keystone species, having effects on ecosystem function far out of proportion to their numbers. Others are ecosystem engineers, physically modifying environments in ways that affect countless other species. The gray wolf provides a perfect example of how a single species can structure entire ecosystems. When wolves were eliminated from Yellowstone National Park in the 1920s, deer populations exploded. Without predation pressure, deer overgrazed young trees and shrubs, preventing forest regeneration. Stream systems changed course because the vegetation that stabilized riverbanks disappeared. Bird populations declined due to habitat loss. Small mammal communities collapsed. When wolves were reintroduced in 1995, the entire ecosystem began to reorganize. Deer populations declined and changed their behavior, avoiding areas where they were vulnerable to wolf attacks. Trees and shrubs began recovering in these areas. Stream systems stabilized as vegetation returned. Bird and small mammal populations rebounded. The wolves had triggered what ecologists call a trophic cascade, effects that rippled through the entire food web. This is happening worldwide as keystone species disappear. Large predators like lions, tigers, sharks, and eagles are vanishing from ecosystems around the globe. Their absence allows prey species to increase beyond the carrying capacity of their environments, leading to habitat degradation that affects countless other species. The loss of large herbivores creates different but equally devastating cascades. Elephants in African savannas are ecosystem engineers that maintain grasslands by preventing forests from encroaching. They create water holes that other species depend on during dry seasons. They disperse seeds across vast distances, maintaining plant genetic diversity. As elephant populations crash due to poaching, entire savanna ecosystems are shifting toward woodland, with consequences for hundreds of other species. Marine ecosystems are experiencing particularly severe cascade effects. Coral reefs support about 25% of all marine species, despite covering less than 1% of the ocean floor. When corals die due to bleaching, warming waters, or ocean acidification, they don't just disappear, they take entire communities with them. Fish populations crash, affecting both marine ecosystems and human communities that depend on fishing. The collapse of large fish populations has triggered cascades throughout ocean food webs. The decline of cod in the North Atlantic led to explosions of small fish and invertebrates that cod used to eat. These changes affected seabird populations, marine mammal distribution, and the entire structure of North Atlantic marine ecosystems. Pollinator collapse provides perhaps the most visible example of ecosystem cascade effects on land. Bees, butterflies, and other pollinators are declining rapidly due to habitat loss, pesticide use, disease, and climate change. About 35% of global food production depends on animal pollination. As pollinator populations crash, wild plant communities are already showing signs of reproductive failure. The economic value of ecosystem services, the benefits that functioning ecosystems provide to humans, has been estimated at $125 trillion. Annually, nearly twice the global GDP. These services include pollination, water purification, climate regulation, soil formation, pest control, and flood protection. As ecosystems collapse, these services disappear, often requiring expensive technological replacements that are less effective than the natural systems they replace. Island ecosystems provide particularly clear examples of how cascading extinctions can completely transform environments. When Polynesian settlers first reached Pacific Islands, they brought with them pigs, rats, and other invasive species. These introductions triggered waves of extinction among native birds, many of which were flightless and had evolved without mammalian predators. The loss of these birds had unexpected consequences. Many were important seed dispersers for native plants. Without them, native forests began to decline, unable to reproduce effectively. Invasive plants moved into the degraded habitats, further altering ecosystem structure. Today, many Pacific islands bear little resemblance to their pre-human ecosystems. Climate change is accelerating cascade effects by adding new stresses to already damaged ecosystems. As temperatures rise and precipitation patterns change, species are forced to migrate, adapt, or face extinction. But in a world where habitats are fragmented and ecosystems are already stressed, many species have nowhere to go. The timing of biological events flowering, breeding, migration is being disrupted by changing climate patterns. If flowers bloom before pollinators emerge, or if birds migrate after their food sources have peaked, the relationships that hold ecosystems together begin to break down. These phenological mismatches are creating new cascade effects as species lose their evolutionary partners. Ocean acidification, caused by increased carbon dioxide absorption, is creating its own cascade effects. As seawater becomes more acidic, shell-building organisms like corals, mollusks, and some plankton struggle to maintain their calcium carbonate structures. The decline of these organisms affects everything from tropical reefs to the base of oceanic food webs. Freshwater ecosystems are experiencing some of the most severe cascade effects. Dams fragment river systems, preventing fish migration and altering flow patterns. Pollution and nutrient runoff create dead zones where nothing can survive. Climate change is altering precipitation patterns, causing some rivers to dry up while others flood more frequently than ever before. The cascading effects of the sixth extinction create a feedback loop that accelerates biodiversity loss. As ecosystems become simpler and less stable, they become more vulnerable to additional disturbances. A diverse ecosystem might absorb the loss of several species without major changes, but a simplified ecosystem can collapse completely if one or two key species disappear. This creates what scientists call an extinction vortex. Once ecosystems begin to unravel, the process becomes self-reinforcing. Species losses beget more species losses. Habitat degradation makes remaining habitats more vulnerable. The collapse accelerates until it reaches a new, much simpler state that may be stable but supports far fewer species. Understanding cascade effects helps explain why conservation efforts often focus on protecting entire ecosystems rather than individual species. Saving a single endangered species is important, but if the ecosystem that supports it is collapsing, the conservation effort may ultimately fail. Successful conservation requires maintaining the complex relationships that keep ecosystems functioning. The domino effect of the sixth extinction also explains why the current crisis is potentially more devastating than previous mass extinctions. In the past, mass extinctions primarily affected individual species through direct environmental stress. Today's extinction crisis is dismantling the relationships between species, potentially making recovery much more difficult. When ecosystems collapse, they don't just lose species, they lose the evolutionary information encoded in the relationships between species. This represents millions of years of evolutionary experimentation that cannot be quickly replaced. Even if we could bring extinct species back through genetic engineering, rebuilding the complex ecological relationships that make ecosystems function would take millennia. The sixth extinction is revealing just how interconnected life on Earth really is. Every species loss sends ripples through the web of life, and we're beginning to understand that our own survival depends on maintaining that web's integrity. As ecosystems simplify and collapse, they become less able to provide the services that human civilization depends on. We're conducting a massive, uncontrolled experiment in how much biodiversity we can lose before the systems that support us begin to fail. The results so far suggest that we're approaching dangerous thresholds more quickly than anyone anticipated. Chapter 10. The human factor for over 99% of human existence. We were victims of mass extinction rather than its cause. Our ancestors survived ice ages that decimated countless other species. They endured volcanic winters, climate shifts, and the constant threat of predators that viewed early humans as prey rather than apex predators. The transformation of humanity from extinction victims to extinction agents represents one of the most dramatic reversals in the history of life on Earth. The story begins with our evolution in Africa around 300,000 years ago. Early Homo sapiens were remarkable in many ways. We had larger brains than our ancestors, sophisticated tool-making abilities, and complex social structures. But we were also vulnerable. Archaeological evidence suggests that our species nearly went extinct at least once, possibly multiple times, with global populations dropping to as few as 1,000 breeding individuals. These population bottlenecks were caused by the same forces that had driven mass extinctions throughout Earth's history: climate change, volcanic eruptions, and environmental instability. The Toba supervolcano eruption 74,000 years ago may have brought our species to the very edge of extinction, creating a genetic bottleneck whose effects are still visible in human DNA today. What saved us, and what would eventually make us the most dangerous species on Earth, was our unprecedented ability to adapt through culture rather than just genetics. While other species required thousands or millions of years to evolve new traits in response to environmental challenges, humans could develop new technologies, strategies, and social organizations within a single generation. This cultural evolution accelerated around 70,000 years ago in what anthropologists call the Great Leap Forward, or Upper Paleolithic Revolution. Archaeological evidence shows a sudden flowering of sophisticated tools, art, jewelry, and complex hunting strategies. More importantly, humans began to demonstrate an ability to cooperate in large groups and plan for future contingencies in ways that no other species had ever managed. These abilities allowed humans to survive and spread across the globe during one of the most challenging periods in Earth's recent history. As we migrated out of Africa and into Asia, Europe, Australia, and eventually the Americas, we encountered environments that would have defeated any other large mammal. We adapted to Arctic conditions that killed off most other large species. We crossed vast oceans to reach remote islands. We learned to live in deserts, rainforests, mountains, and tundra. But our success came at a cost that wouldn't become apparent until much later. Wherever humans arrived, especially in environments where large mammals had never encountered human hunters, extinction rates spiked dramatically. The pattern was so consistent that paleontologists can often predict when humans first reached a new continent simply by looking at when large mammal extinctions began. The mechanism wasn't just direct hunting, though that played a major role. Humans were hyperkeystone species. Our impacts on ecosystems far exceeded what would be expected based on our population size alone. We used fire as a landscape management tool, fundamentally altering vegetation patterns across entire continents. We introduced new species to islands and continents where they had never existed. We modified water sources, hunting patterns, and migration routes. Perhaps most significantly, we began to systematically eliminate large predators that competed with us or threatened our safety. Lions, bears, wolves, and other apex predators that had shaped ecosystems for millions of years were driven to extinction or near extinction across vast regions. This had cascade effects throughout entire food webs, as we saw in the Yellowstone wolf example. The invention of agriculture around 10,000 years ago, marked the beginning of humanity's transformation from a biological species to a geological force. Agriculture allowed human populations to grow exponentially and gave us the ability to modify landscapes on unprecedented scales. Ever since the beginning of the pollutant-pumping Industrial Revolution in 1760, humans have been the main contributor to Earth's current environmental crisis. From a planetary perspective, the Industrial Revolution was the moment when human impact shifted from regional to global. Suddenly, we could extract resources from the deep earth, synthesize chemicals that had never existed in nature, and produce waste products at scales that overwhelm natural recycling systems. We began to alter the fundamental chemistry of the atmosphere and oceans. The numbers that describe modern human impact read like science fiction. We have moved more earth and rock through mining than all the world's rivers combined. We have created synthetic compounds that will remain in Earth's geological record for millions of years. We have altered the chemical composition of the atmosphere, changing global climate patterns. We have diverted more than half of all accessible fresh water for human use. Our impact extends beyond Earth's surface. We have created artificial light, pollution that disrupts migration patterns and biological rhythms across the globe. We have filled near-Earth space with debris from satellites and rockets. We have even begun to alter the magnetic field around Earth through our electronic activities. What makes humans uniquely dangerous as an extinction agent is our combination of rapid technological development with slow evolutionary adaptation to our own power. Our brains evolved to handle the challenges of small group survival in African environments, not global resource management or long-term ecological planning. We're running 21st century technology on cognitive hardware designed for hunter-gatherer societies. This creates systematic biases in how we perceive and respond to environmental problems. We're excellent at recognizing immediate, local threats, but poor at responding to gradual, global changes. We can mobilize massive resources to fight wars that last years but struggle to address environmental problems that unfold over decades. We're motivated by competition with other humans, but often ignore non-human consequences of our actions. Modern economic systems amplify these problems by rewarding short-term profit over long-term sustainability. Companies that destroy natural resources to maximize quarterly profits outcompete those that invest in long-term environmental stewardship. Political systems reward leaders who deliver immediate benefits over those who make sacrifices for future generations. The result is a species that has become incredibly powerful without developing the wisdom to use that power responsibly. We can split atoms and engineer genetics, but we're still struggling to manage our own population growth and resource consumption. We can send robots to Mars, but can't prevent the destruction of our own planet's forests. This disconnect between power and wisdom explains why the sixth extinction is different from all previous mass extinctions. Previous extinctions were caused by external forces, asteroids, volcanoes, climate changes that operated without intention or awareness. The sixth extinction is being caused by an intelligent species that theoretically has the knowledge and technology to prevent it. Yet the same traits that made humans successful survivors are now making us dangerous to global ecosystems. Our ability to cooperate in large groups becomes problematic when those groups compete for limited resources. Our skill at exploiting environments becomes devastating when applied with industrial technology. Our capacity for rapid cultural change becomes dangerous when it outpaces our ability to understand consequences. Human population growth exemplifies this problem. It took all of human history until 1800 for our population to reach 1 billion. We added the second billion in 130 years, the third billion in 30 years, and we're now adding billions every 10 to 15 years. This exponential growth is straining Earth's ecosystems beyond their ability to recover. Consumption patterns amplify the population effect. The average American uses 50 times more resources than the average person in developing countries. If everyone consumed at American levels, we would need 5 Earth-sized planets to sustainably support the current human population. This inequality means that relatively small populations in wealthy countries have disproportionate environmental impacts. Climate change represents the ultimate expression of humanity's role as an extinction agent. By burning fossil fuels, we're altering global climate patterns faster than most species can adapt. We're creating conditions that haven't existed for millions of years, forcing species to either evolve rapidly, migrate vast distances, or face extinction. The feedback loops we've created are particularly dangerous. As forests burn due to climate change, they release more carbon dioxide, accelerating warming. As Arctic ice melts, it exposes dark ocean water that absorbs more heat than reflective ice. As permafrost thaws, it releases methane and carbon dioxide that have been frozen for thousands of years. Yet, humans also represent the only hope for preventing or limiting the sixth extinction. No previous extinction agent could recognize what it was doing or choose to stop. No asteroid ever developed a conscience about its impact. No volcano ever decided to reduce its emissions for the good of the biosphere. For the first time in Earth's history, the species causing a mass extinction is also capable of understanding extinction processes, predicting their consequences, and potentially preventing them. We have the scientific knowledge to understand what's happening. We have technologies that could reduce our environmental impact. We have communication systems that allow global coordination of conservation efforts. The question is whether we can overcome the psychological, economic, and political barriers that prevent us from acting on this knowledge. Can we develop economic systems that value long-term environmental health over short-term profit? Can we create political institutions capable of making decisions on the timescales required for environmental protection? Can we change cultural values to prioritize ecological sustainability? The transformation of humans from extinction victims to extinction agents wasn't inevitable. It was the result of specific choices about how to use our unique capabilities. The next phase of human evolution may depend on whether we can make different choices about our relationship with the natural world. This is the central paradox of the sixth extinction. The same intelligence that created the crisis may be the only thing capable of solving it. Whether humanity becomes the first species to deliberately prevent its own extinction event, or the first intelligent species to consciously destroy the biosphere that sustains it, remains to be seen. Chapter 11. Hope in the Darkness. In 1987, there were only 27 California condors left on Earth. These magnificent birds, with wingspans of nearly 10 feet, had ruled the skies of western North America for thousands of years. They had survived ice ages, climate changes, and the arrival of humans. But they couldn't survive lead poisoning from hunters' bullets, habitat destruction, and collisions with power lines. The species was 3 weeks away from complete extinction. Today, there are over 500 California condors, with more than half flying free in the wild. Their recovery represents one of conservation's greatest success stories and proof that even species on the very brink of extinction can be brought back. The Condor program demonstrates something crucial about the sixth extinction. While we are causing unprecedented biodiversity loss, we also have unprecedented power to prevent it. The California condor recovery required a massive, coordinated effort involving multiple government agencies, zoos, universities, and conservation organizations. Every remaining wild condor was captured and brought into captive breeding programs. Scientists had to learn everything about condor biology, behavior, and ecology. They developed artificial insemination techniques, hand-rearing protocols, and methods for teaching captive-bred condors how to survive in the wild. The program cost over $100 million and took decades of intensive effort. Lead ammunition was banned from condor habitat. Power lines were modified to prevent electrocutions. Nest sites were protected and monitored. Every released condor was tagged and tracked. The result is a species that was essentially extinct and is now breeding successfully in the wild for the first time in decades. The condor story illustrates several key principles of successful conservation. First, it's possible to bring species back from the very edge of extinction with sufficient resources and commitment. Second, successful conservation requires addressing the root causes of decline, not just protecting the remaining individuals. Third, conservation works best when it combines scientific research, technological innovation, and community engagement. These principles have been applied successfully to dozens of other species around the world. The black-footed ferret was once considered the most endangered mammal in North America, with only 18 individuals remaining in the wild. Through captive breeding and habitat restoration, there are now over 300 black-footed ferrets in the wild across 8 states. The Arabian oryx became completely extinct in the wild in 1972, surviving only in captivity. Coordinated breeding programs in zoos around the world built up captive populations, and the species was successfully reintroduced to the wild starting in 1982. Today, there are over 1,000 Arabian oryx in the wild, the first species ever to move from extinct in the wild back to vulnerable on the IUCN Red List. Marine conservation has achieved equally dramatic successes. Humpback whale populations were reduced to perhaps 5,000 individuals worldwide by commercial whaling. Following international protection beginning in 1966, humpback populations have recovered to over 80,000 individuals. Some regional populations have increased by 10 to 12% annually for decades. The gray whale provides an even more remarkable recovery story. The Eastern Pacific population was hunted to near extinction twice, once in the 1800s and again in the early 1900s. After receiving protection, the population recovered so successfully that it was removed from the U.S. Endangered Species List in 1994. From fewer than 2,000 individuals, the Eastern Pacific gray whale population grew over 26,000. These large-scale recoveries demonstrate that marine ecosystems retain remarkable resilience when given the chance to heal. Marine protected areas, fishing quotas, and international agreements have allowed depleted fish stocks, coral reefs, and marine mammal populations to recover in many regions. Habitat protection and restoration have achieved conservation successes. On landscape scales, the reforestation of large areas in Costa Rica, South Korea, and parts of the eastern United States shows that degraded ecosystems can be restored to support diverse wildlife communities. Yellowstone's wolf reintroduction demonstrates how restoring key species can help entire ecosystems recover their natural functioning. Island restoration projects have achieved some of the most dramatic conservation successes by removing invasive species and allowing native ecosystems to recover. On islands around the world, the removal of introduced rats, goats, pigs, and other invasive mammals has led to remarkable recoveries of native plants and animals. On Anacapa Island off the California coast was overrun by introduced rats that were eating seabird eggs and destroying native plant communities. After the rats were eradicated, native plants began recovering immediately. Seabird populations exploded as they could finally breed successfully. Within a decade, The island's ecosystem had largely returned to its natural state. The recovery of several bird species shows how targeted conservation efforts can address specific threats. DDT nearly drove bald eagles, peregrine falcons, and brown pelicans to extinction in North America by causing eggshell thinning. After DDT was banned and captive breeding programs were established, all three species have recovered dramatically. Bald eagles, once reduced to fewer than 1,000 breeding pairs, now number over 300,000 individuals. International cooperation has been crucial for many conservation successes. The Montreal Protocol, which phased out ozone-depleting chemicals, prevented what could have been an ecological catastrophe. The ozone hole is now healing, and countless species have been saved from the effects of increased ultraviolet radiation. CITES, Convention on International Trade in Endangered Species, has successfully reduced pressure on many endangered species by regulating international trade. While enforcement remains challenging, CITES has contributed to the recovery of species like African elephants in some regions, several whale species, and many endangered plants and animals. Technological innovations are creating new possibilities for conservation. GPS tracking allows scientists to understand animal movements and habitat needs in unprecedented detail. Genetic techniques help manage small populations and identify distinct populations that need protection. Camera traps and acoustic monitoring enable non-invasive wildlife surveys. Satellite imagery helps monitor habitat loss and the effectiveness of protected areas. Emerging technologies like environmental DNA, eDNA sampling can detect rare species from water or soil samples, making it possible to monitor biodiversity in remote or inaccessible areas. Drone technology allows researchers to survey wildlife populations and monitor illegal activities like poaching and logging. Artificial intelligence helps analyze vast amounts of ecological data to identify conservation priorities and predict species responses to environmental change. Community-based conservation has achieved remarkable successes by involving local people as partners rather than obstacles in conservation efforts. In Namibia, community conservancies that give local communities rights to manage and benefit from wildlife have led to dramatic increases in populations of elephants, rhinos, and other large mammals. The recovery of mountain gorillas in Rwanda demonstrates how conservation can benefit both wildlife and human communities. Tourism revenue from gorilla viewing has provided economic incentives for local communities to protect the forests, while anti-poaching efforts have created jobs for local people. Mountain gorilla populations have increased from fewer than 250 individuals in the 1980s to over 1,000 today. Payment for ecosystem services programs compensate landowners for maintaining forests, wetlands, and other ecosystems that provide benefits, like carbon storage, water purification, and biodiversity conservation. These programs create economic incentives for conservation, while providing income for rural communities. Urban conservation efforts show that biodiversity can recover even in highly modified environments. Green roofs, urban parks, and wildlife corridors in cities provide habitat for many species. Some cities have become refuges for species that are declining in rural areas due to agricultural intensification. The recovery of several fish species in urban rivers demonstrates that aquatic ecosystems can bounce back with improved water quality. Management. Salmon have returned to rivers in Seattle, London, and other major cities after decades of absence. Otters are recolonizing urban waterways across Europe as water quality improves. These success stories share common elements that point toward broader strategies for addressing the sixth extinction. Most required sustained, long-term commitment over decades. They combined scientific research with practical conservation action. They addressed root causes of decline rather than just symptoms. They often involved multiple organizations working together across jurisdictional boundaries. Successful conservation also requires adequate funding, political support, and public engagement. The most successful programs have combined government resources with private funding and volunteer efforts. They have maintained public support by demonstrating tangible results and connecting conservation to human values and interests. Perhaps most importantly, these successes demonstrate that the sixth extinction is not inevitable. While the scale of the current crisis is unprecedented, so is our capacity to understand and address it. We have scientific knowledge about ecosystem functioning that no previous generation possessed. We have technologies for monitoring and managing wildlife populations that would have seemed magical just decades ago. We have global communication systems that allow conservation efforts to be coordinated across continents. The challenge is scaling up these successes to match the scale of the crisis. The same approaches that have saved individual species can potentially save entire ecosystems if applied with sufficient resources and commitment. The question is whether human society can mobilize the will and resources necessary to implement conservation at the global scale required to prevent mass extinction. These success stories provide hope, but they also highlight the enormous effort required to prevent extinctions in the current era. Every conservation success represents thousands of hours of scientific research, millions of dollars in funding, and years or decades of sustained effort. If we are to prevent the sixth extinction, we need to scale up these efforts by orders of magnitude. Chapter 12. The tipping point. There's a moment in every avalanche when individual snowflakes stop mattering. One snowflake, then another, then thousands, until suddenly, the entire mountainside is in motion and nothing can stop it. Earth's climate and ecological systems have their own avalanche moments, points where gradual change becomes irreversible collapse. Scientists call these tipping points, and we may be approaching several of them simultaneously. Understanding tipping points is crucial to grasping the true danger of the sixth extinction. Unlike gradual decline, tipping point failures happen rapidly and are often impossible to reverse, even if the original stressors are removed. They represent the difference between a crisis we can still manage and a catastrophe we can only survive. The Amazon rainforest provides perhaps the most visible example of a system approaching its tipping point. For millions of years, the Amazon has been what scientists call a self-reinforcing system. The forest creates its own weather patterns, recycling moisture from the Atlantic Ocean inland through transpiration. Trees release water vapor that forms clouds, which produce rain that feeds more trees. It's a biological engine that has maintained itself for millennia. But this engine is beginning to break down. Large areas of the Amazon are now releasing more carbon dioxide than they absorb, fundamentally altering their role in the global climate system. Deforestation has reduced the forest's ability to generate its own rainfall. Climate change is bringing more frequent and severe droughts. Scientists estimate that if the Amazon loses another 10 to 15% of its original area, the entire system could collapse into savanna within decades. The consequences would be global. The Amazon stores about 10% of all carbon in terrestrial ecosystems. Its collapse would release massive amounts of greenhouse gases, accelerating climate change worldwide. The loss of the Amazon's weather-making capacity would disrupt precipitation patterns across South America. Countless species found nowhere else on Earth would vanish forever. Arctic sea ice represents another critical tipping point. For hundreds of thousands of years, Arctic ice has acted as Earth's air conditioner, reflecting sunlight back to space and keeping global temperatures stable. As the ice melts due to warming temperatures, it exposes dark ocean water that absorbs heat rather than reflecting it. This creates a feedback loop. Less ice means more warming, which means even less ice. the Arctic is warming twice as fast as the rest of the planet, and summer sea ice has declined by over 40% since satellite records began in 1979. Some scientists believe we've already passed the point of no return for Arctic summer sea ice. Even if we stopped all greenhouse gas emissions today, the remaining ice might continue melting for decades due to heat already trapped in the system. The loss of Arctic ice affects far more than polar bears and seals. Arctic ice helps drive global ocean circulation patterns that distribute heat around the planet. Its disappearance could disrupt the Gulf Stream and other currents, potentially triggering rapid climate changes in Europe and North America. The melting also releases methane trapped in frozen Arctic soils, further accelerating global warming. Coral reef systems worldwide are approaching their own tipping points. Coral reefs are incredibly sensitive to temperature changes. Just a 1 to 2 degree increase in ocean temperature can trigger mass bleaching events that kill entire reef systems. As ocean temperatures continue to rise and oceans become more acidic due to increased carbon dioxide absorption, many reefs are experiencing back-to-back bleaching events with no time to recover. The Great Barrier Reef has experienced 5 mass bleaching events since 1998, with the most recent 3 occurring in just 5 years. Scientists estimate that the reef has lost over half its coral cover since the 1990s. Beyond a certain threshold of warming and acidification, coral reefs may be unable to survive at all, regardless of other conservation efforts. The collapse of coral reefs would eliminate habitat for about 25% of all marine species. Coastal communities that depend on reefs for fish protein and storm protection would face food security and safety crises. Tourism economies built around reef diving and snorkeling would collapse. The economic impact could reach hundreds of billions of dollars globally. Soil systems represent a less visible but equally critical tipping point. Healthy soils contain more carbon than the atmosphere and all land vegetation combined. They support 95% of global food production and host more biodiversity than any other ecosystem on Earth. But intensive agriculture, deforestation, and climate change are degrading soils at unprecedented rates. The world is losing soil 10 to 40 times faster than it can be naturally replenished. At current rates, we have only 60 years of topsoil left globally. Beyond a certain threshold of degradation, soils can enter a death spiral where they lose their ability to hold water, support plant growth, or store carbon. Degraded soils become sources of greenhouse gases rather than carbon sinks, accelerating climate change. Ocean circulation patterns face their own tipping points. The global ocean circulation system, sometimes called the Great Ocean Conveyor Belt, distributes heat and nutrients around the planet. This system is driven by differences in water temperature and salinity. As polar ice melts and adds fresh water to the oceans, and as global temperatures rise, this circulation system is beginning to slow down. The Atlantic meridional overturning circulation, AMOC, which includes the Gulf Stream, has already slowed by about 15% since the mid-20th century. If it slows much more or shuts down entirely, it could trigger rapid cooling in Europe while accelerating sea level rise along the U.S. East Coast. Previous OC shutdowns have been associated with dramatic climate changes that happened within decades rather than centuries. Perhaps most concerning is that these tipping points don't operate in isolation. They interact with and amplify each other. The loss of Arctic ice accelerates Amazon deforestation by changing precipitation patterns. Soil degradation reduces the land's ability to absorb carbon, accelerating climate change that destroys coral reefs. Ocean circulation changes affect global weather patterns that influence all terrestrial ecosystems. This interconnectedness means we could be approaching what scientists call a tipping point cascade. where crossing one threshold triggers others, in a domino effect that transforms the entire Earth system. Some researchers believe we may have only 10 to 20 years to prevent such a cascade from beginning. The social and economic implications of ecological tipping points are staggering. The collapse of major food-producing regions could trigger mass migration and political instability. The loss of ecosystem services like water purification and flood control could cost trillions of dollars to replace with technology. Climate. Refugees could number in the hundreds of millions. Yet, understanding tipping points also reveals opportunities for intervention. Because tipping point systems are often highly sensitive to small changes, targeted interventions can sometimes have outsized effects. Protecting key forest corridors might prevent ecosystem fragmentation. Restoring wetlands can help maintain regional water cycles. Reducing specific pollutants can help ecosystems maintain their resilience. The race to prevent tipping point cascades is perhaps the greatest challenge humanity has ever faced. Unlike gradual environmental changes that allow time for adaptation, tipping points demand immediate action. Once crossed, they transform the rules of the game entirely, often making previous conservation strategies obsolete. The window for preventing the most dangerous tipping points may be measured in years rather than decades. Every month of delay makes the interventions required more expensive and less likely to succeed. The choices we make in the next few years about energy systems, land use, and conservation could determine whether future generations inherit a stable, resilient planet or a chaotic, unpredictable one. We stand at the edge of a cliff, not yet fallen but no longer on entirely solid ground. Whether we step back to safety or tumble into an uncertain future depends on actions we take today.